Okay, so welcome back to the second part about binary choice models. So those are the models that I already mentioned in the very beginning. Yeah, so kind of where we model, for instance, a decision-making process, or we generally have some variable that is coded as 0, 1. Yeah, it's 0 when we talk about a failure, or 1 if we talk about a success. Yeah? Okay, so the goal is to model the probability of success given some x variables, so given some covariates, given some explanatory variables. Now, why? So this is a Bernoulli distributed variable because it's 0, 1. And just kind of plugging in the definition of the expectation here. Yeah? So the expectation is we have to take a look at the values that y takes. So 0 times the probability of y being 0 plus 1 times the probability of y being 1. And therefore, we have seen that the conditional expectation actually coincides with the conditional probability of being 1, conditional on the x's, of course. Yeah. So this is because we are looking at a binary choice model that is coded as 0, 1. Okay. Now, what is the motivation in many cases of binary choice? Well, we can model like 0, 1 models directly. Yes, okay, we model yes or no questions, but many times binary choice is motivated using these latent variable models. Yeah, so for instance, we imagine that there is some unobserved variable yt star, but we can only observe a certain part of it. Yeah, so for instance, let's say kind of you're a firm and you're deciding whether to innovate, yes or no. Yeah, then kind of like this decision to innovate will be a yes whenever kind of like the additional sales or the additional revenue that you're expecting is positive. So kind of like the expected revenue gain would be, for instance, then yt star. This is in principle a continuous variable. However, you don't see it. Yeah, so this would be the true model, and you would like to see yt star, but you don't. So the only thing that you can observe is whether or not the firm conducts innovation. Yeah. So you basically only observe y, which well is 1, if the, as I said here, the expected returns from innovation are positive, or 0, well, if they're at least at maximum 0, right? Okay, now let's assume that the model error, this epsilon it here, has a distribution that is symmetric around 0. Yeah, so that is not really costly. Yeah, so as long as we kind of include a constant regressor in the axis. Yeah, and we also assume that it's continuous. When we do that, we immediately see that, well, I mean, from here to here, we just plug in the definition of yit. Yeah? Here we plug in the definition of yit star. Here we simply take epsilon to one of the sides. Yeah? Then, well, this is just a definition of the CDF. Yeah, so kind of like this bigger than some number is just 1 minus the CDF at that number. And because this thing is symmetric around 0, this is the same thing as this. Okay. Yeah, so in total, what we get is that, well, the conditional expectation of y being 1. Sorry, this is actually, this is a small mistake. I'm gonna fix that immediately. So we don't need so the conditional expectation of y given x is the probability of y being 1, conditional on x, and is given by this f of xt prime theta. Yeah, so kind of comparing with the linear regression model, in the linear regression, we really kind of assume that this f is the identity. Okay, good. Now, there are certain consequences, of course, that now we allow for nonlinear functions. Yeah? So kind of that we don't have a linear function here, but rather a potentially nonlinear function of both the axis and the parameters. So for instance, we are typically interested in the marginal effect. So what is kind of the effect of marginally increasing one of the x variables, for instance, the kth component here. Yeah, it turns out that in a linear model, the marginal effect is just the same as the parameter. Also kind of when you kind of take the derivative with respect to some component, of theta here. It's just some component of x here. It's just a parameter. Easy. In nonlinear models, you see we get the parameter times the derivative of this big F, which I denote here as little f. Right. So remember that this is a CDF, so this is going to be a PDF. Okay. What you see here is that the marginal effect depends, well, on the parameter. It depends, however, also on the axis. Yeah? So kind of like depending on which x you plug in, the marginal effect will be different. Yeah? So kind of, for instance, if x is very large, the marginal effect may be very different from when x is very small. Therefore, it's okay, so that's what I just said. The marginal effects are not constant, yeah? So it depends on the parameter and on the x variables. Yeah? When the component of x is discrete, for instance, when you have a dummy variable, then you typically look at the 1 unit increase. So kind of the marginal effect that you're interested in is basically, well, the f when this is +1, right? Versus the same f when the original x. I hope this is sufficiently clear. Another thing to notice is that the PDF, this thing, is always positive. And therefore, the sign of theta will give you the sign of the marginal effect. So if this thing is positive, that means like the marginal effect is also positive. However, the overall magnitude of the effect, that still depends on which data you plug in and on the remaining parameters. Yeah? So kind of the effect of one variable also depends on the parameter of another variable. So what you can do is, for instance, compare relative marginal effects. Yeah? So kind of if you look at the marginal effect of the cave component versus the ELF component, and you just plug in all the formulas, you will see that this will be the outcome. So kind of if the final outcome is 2, then you will find that, of course, like a marginal increase in the cave component of x is twice as important or has twice as large effect as the marginal increase in the ELF component. Moreover, it's sort of very easy to find an upper bound of the magnitude by just simply taking a soup over this density. So for instance, like the soup can be 0.6, then you know that the marginal effect will be bounded by 0.6 times theta k, for instance. Generally, however, people decide they don't like that the marginal effects depends on the data. So kind of when you want to summarize a data set, and you want to report only a couple of numbers, then you need to find a way how to kind of get rid of this dependence on the data. So what people do is that they evaluate the marginal effects at some meaningful values, or they just average out the partial effect. So kind of this is like the most popular choice, the average partial effect, where you look at the partial effect of the cave component, and you just average that across all values that x takes in your data set. That's one way of doing it. That's the APE, but it's not the only choice. Yeah? So, for instance, here the averaging is done on the outside, but you could also think of using basically you just evaluate the margin effect at the sample mean or at the median or some other meaningful value. Yeah, then you kind of do the averaging on the inside before you kind of apply this F. Yeah? It's not necessarily the same, of course, but both values make sense depending on the application at hand. Yeah, but again, like the APE, that's probably the most popular choice. Now, because we have such a structural model, kind of where we assume a certain density is true, we should also gain something. Yeah, so kind of like nonlinearity is not necessarily bad. Yeah? So nonlinearity can give you useful information because you can actually compute marginal effects at a large range of values. Yeah? So for instance, you can look at the marginal effects in each quantile or of the data, for instance, yeah, or like 20%, 40, 50, whatever. You can compute all these marginal effects, and this can be very useful. Yeah? So you can, so for instance, see that the marginal effect of education for low-income people is much larger than for high-income people, for instance. Yeah? So all these things can be interesting. And yeah, whenever you have to estimate the APEs and all this kind of stuff, well, I mean, wherever you see a theta, you put a head on it, which means you just replace it with the MLE. That's as simple as it gets, I think. Okay, now the two by far most popular choices for binary, binary variables are logit and probit. Yeah, so kind of this f function is sometimes called the link function. And if we choose f to be the standard normal CDF, then we arrive at the probit model. And if we choose f to be the logistic CDF, then we arrive at the logit model. Now, the logistic CDF looks pretty much like the normal CDF. It just has flatter tails. So the normal CDF has more meat on the outside. Now, there is actually very little guidance on how to choose between the two models. In practice, it's pretty much the same. They give you pretty similar outcomes. Yeah? So kind of, for instance, the APEs, they are pretty similar. They don't differ much. And if you look at the coefficients themselves, there is like a rule of thumb that says that the logit coefficients are about 1.6 times as large as the probit coefficient estimates. And the rule of thumb is actually based on, it's very crude. So it's based on the ratio at 0, because both distributions are symmetric around 0 and they have their maximum at 0. And this is where it comes from. Yeah, so kind of as long as your data is relatively close to the center, this rule of thumb is pretty accurate. Okay, so that's this. The logit is sometimes preferred, especially kind of like in biostatistics. People often prefer the logit because it can be interpreted as log odds ratio. That's kind of what are the odds. Well, the odds is simply the ratio of the probability of success divided by the probability of failure. Again, this is just P by definition here. And because it's binary, Y, that means like the probability of failure has to be 1 minus P. Okay. Log odds simply means, well, we take the log of the odds and that's it. So kind of, if we kind of look now at this log odds and we assume a linear model in XIT, then we basically arrive at the logit model. So I'm not going to go through all these equations here. You can do that yourself. So basically, if you want to have a log odds interpretation and you're willing to make a linearity assumption on the log odds, then you arrive automatically at the logit model. So kind of the same does not apply to probit. That's just a warning. Okay. Now, yeah, how would we estimate this? So kind of, well, we basically, so here is kind of again the model. We have a latent variable. We observe only like whether this latent variable is bigger than 0 or not. And we make some distributional assumption on the model error. So we say it's IID, and we have a distribution that is symmetric and with a nice CDF. Oh, okay. Then we get to the marginal PMF, the probability mass function of YIT. So mass function, because YIT is binary, is just this. So kind of whenever YIT is 1, we get this part. And whenever YIT is 0, we get this part. And yeah, that's pretty much it. So by independence across INT, we just calculate the joint likelihood. It's the same thing always. So kind of the only thing that we add are these two products here. But however, we would kind of look at the log likelihood whenever we maximize anyway. So notice that this likelihood here is a conditional likelihood. So that's what I say here. because we are making a conditional distributional assumption. Yeah? So kind of we make an assumption on the distribution of epsilon conditional on the XITs. We also implicitly assume strict exogeneity as we did in linear panel data models. Yeah, so actually we're making strictly stronger assumptions here. Yeah? So you can see here, yeah, pretty much this is just like an explanation why we have implicitly assumed strict exogeneity, just an instance of the law of iterated expectations, or the Tower rule, if you want to call it that way, or the smallest information wins property. And notice also that we really make super strong assumptions here. So kind of we really assume that we know the distribution of epsilon IT. In that case, we call this model fully parametric. So because the only thing that we don't know is the parameter itself. Later on in the next lecture, we will look at what we call semi-parametric models, because there will be an unobserved effect of that. We will not necessarily know the distribution. Yeah? So then kind of, it's not just the parameter itself that is unknown, but some aspect of the distribution itself is also unknown. Then we say it's non-parametric or semi-parametric. Okay, so the next sentence simply says that, well, I mean, if we know the distribution of epsilon IT, we implicitly assume that not only the mean is correctly specified, but also the variance, the kurtosis, the whatever, everything is correctly specified. Yeah? That's of course a very strong assumption. Yeah? So kind of what people do in practice in order to check whether these assumptions are sort of robust to slight changes, to deviations from these assumptions. They would estimate the coefficients using a parametric model, but then would kind of use a robust sandwich type estimator for the standard errors. Now, Stata has buttons for that, and I think later on we will also take a look at how to do this. Okay. So from 6 we get the log likelihood, and we just calculate the MLE. And in logit and probit, something important to know is that, well, there's no closed form. We cannot derive an explicit form for the maximum likelihood estimator, and everything has to be done numerically. So on the popular routines are, for instance, Newton-Raphson. That's a maximization routine that you can, for instance, implement in R. Okay. Now, logit and probit, the likelihood is strictly concave under a certain simple condition. Yeah, so kind of if this holds. So if this is basically, how do you say, yeah, you know, this is a condition that we had before. Yes. So why is this important? Well, first of all, that's good for the numerical optimizers, because like the maximizer will be unique. There's going to be a global maximum rather than kind of a function that goes like this. So then we have like multiple local maximizers, and the Newton-Raphson algorithm is not guaranteed to converge to the actual overall maximizer. But here, logit probit, that's not a problem. If you find the maximizer, you know it's going to be the global maximizer. And the next couple of slides, I don't really want to talk so much about it because, well, it's just formulas. You can do, you can go through the derivations yourself. I hope everything is correct. Yeah. If you find a mistake, please let me know. So kind of what you would do is that you would find the first order condition. It's simply say, again, taking the derivative, evaluating at the MLE, and this has to be 0. And now you can, for instance, use a root finding routine that solves this thing for theta hat. You cannot solve this explicitly, of course. Everything will have to be done numerically. Okay, next thing is estimating the variance. So for that, we know that we can either take a look at like the outer product of the score. Remember that was the definition of the Fisher information. But because we are in a likelihood setting, we know that the information equality holds. Therefore, we can simply look at the matrix of second derivatives. Remember that the variance is the inverse Fisher information. And the Fisher information was simply the negative of the second derivative of the likelihood in expectation. So again, here is just calculation, it's just formula, but this is basically the second derivative. Notice that it's truly a k times k matrix. And yes, so if we want to kind of, yeah, okay, so here I kind of write what is the expected Hessian. So that's this slide. I'm just gonna jump a little bit here because the important part is that in likelihood models, you have a couple of options in order to estimate the variance. So for instance, you can calculate the expectation of the likelihood of the Hessian of the likelihood explicitly. And this expression then will depend on unknown values. So because this will depend on theta 0. And whenever in the resulting expression you find a theta 0, well, you replace it by the MLE, and you make this then feasible. You can also simply look at the second derivative of the likelihood evaluated at the MLE. It's also valid as n and t goes to infinity, or actually as n goes to infinity. This will also converge to this thing. Or you can use the definition of the Fisher information, meaning that you really compute the outer product of the scores. So kind of, again, this should remind you of the definition of the Fisher information. And again, as n goes to infinity, it's going to converge to the same thing because of the information equality. So these are three options that you can use in order to estimate the variance in maximum likelihood. Okay, so here, quick break maybe, and then we continue